Okay, so this is a picture of the unit circle, and I want you to take a deep breath, don't have a panic attack. I just showed this to you because we're going to start talking about trigonometric functions. And even though the unit circle is a scary concept, it's actually the best way to think about the trigonometric functions. And it's also the best way to define the trigonometric functions. So what we have here is a circle of radius 1 centered at the origin. And now these angles, if you're more comfortable in degrees, that's fine, but I'll probably stick with radians. These angles are from the positive x-axis. So here's the positive x-axis. And so my angles are going to be increasing counterclockwise, that's important, from the positive x-axis. So I'm going to hit 30, 45, 60, 90, 120. These are just some special values. But my angle, it's very important, is just how much I've rotated from the positive x-axis, counterclockwise. Now if I take a ray at one of these angles, it's going to intersect the unit circle at a point. Now the x-coordinate of that point is defined to be the cosine of that angle, and the y-coordinate is defined to be the sine of that angle. Now you can also define sine and cosine using right triangles. And this really is the same thing, but it's slightly more general because we're going to actually allow our angle to increase or decrease indefinitely. So we want to notice just a few things about the trigonometric functions. First of all, there are other trigonometric functions, but they're all defined in terms of sine and cosine. So recall that we have tangent of theta, but that's just equal to sine theta divided by cosine theta. So there's really not a lot of new information about tangent. Same thing with secant. Secant is just defined to be 1 over cosine theta. Cosecant is defined to be 1 over sine theta. And cotangent theta is just defined to be cosine theta over sine theta. So these are just other trigonometric ratios that sometimes are easier to work with, but notice they really all depend on sine and cosine. We'll also note that cotangent is just 1 divided by tangent theta. So cotangent is sometimes called reciprocal sine. Secant is called reciprocal cosine because it's just the reciprocal. Cosecant is reciprocal sine. But even more is true. Not only are all the other 4 trig functions defined in terms of sine and cosine really aren't that different. And what I mean by that is that if we look at the unit circle, we can notice that if I take an angle, let's say 30 degrees, and I look at the x-coordinate of the intersection, so I look at the cosine of 30 degrees, square root of 3 over 2, and I add 90 degrees, so I go up to 120, then the sine of 90 plus that original angle is going to be equal to the cosine of the original angle. So what I mean is that sine theta is really nothing more than just cosine of theta plus pi over 2, or if you prefer 90 degrees. So sine is really just a translation of cosine, which is really cool. Because really, if we can just understand the basic properties of one of the trig functions, the other ones really are going to follow. And that's something we're going to see in calculus as well. Once we figure out how to do limits with sine, take derivatives with sine, then really the rest is going to follow pretty easily. So this is just an introduction, again, just to remind you of the basic trig functions, sine and cosine, and then the corresponding other trig functions that are defined in terms of sine and cosine, this sort of key identity relating sine and cosine. And all of this is just coming from symmetry in the unit circle. So as we move forward with the trigonometric functions, it's going to be very important for you to have either this unit circle in the back of your mind if you're really comfortable with it, or maybe even find a copy online or in a book so that you can reference it. So I told you that most of the trig functions, actually all of the trig functions, are defined in terms of sine and cosine, and that we can think about cosine as just a translation of sine. So I'm going to talk about just the properties of sine theta, just for a little bit, just to give an introduction. So first of all, the domain of sine theta, so if I define f of theta to be sine theta, the domain of this function, well, recall that an angle on the unit circle can just extend indefinitely if I go counterclockwise, and it can actually extend negatively if I go clockwise. So the domain for my angles really is all real numbers. But now remember that sine theta was the y-coordinate of that intersection point on the unit circle. So the largest y-coordinate on the unit circle will be 1, and the smallest will be -1. And we're going to hit everything in between. So the range of sine is going to be -1 to 1. This is going to be a very important fact, that sine will live in this sort of small interval between -1 and 1. The same is true for cosine. So let's think about sine theta and whether or not it has an inverse, whether or not it's 1 to 1. Well, notice right away that sine theta is not 1 to 1. And again, if you think about the picture of the unit circle, it should be clear that sine of theta is going to be equal to sine of theta plus 2 pi. Because if I add 2 pi to an angle, I end up in exactly the same point in which I started, which will have the same y-coordinate of that intersection point. So sine is not 1 to 1. So we need to restrict the domain to make sine theta 1 to 1. Now, there are more than one ways to do this, but there's a standard way to do it. And so what I'm going to do is I'm going to restrict the domain to -pi/2 to pi/2. And if you're asking me why, well, someone smarter than me said this was the way to do it. And it's really just conventional. A lot of things we'll see from algebra are just conventional. We just want to think about it that way because then we have a kind of consistent way to work on problems. Okay, so on this domain, sine is 1 to 1. And if you want to see why, just look back at the unit circle. As the angle goes from -pi/2 to pi/2, we're getting a unique y-coordinate as we move from those two angles. So on this domain, we can define f inverse as sine inverse of theta. And sometimes it's also called arcsine. Either way is perfectly fine. Arcsine is sort of to remove the ambiguity about this -1, that it's not actually a reciprocal. The reciprocal of sine is cosecant. This is actually the inverse of sine, the function inverse. So when I compose sine and sine inverse, they'll cancel naturally. And so I'm not going to talk about the rest of the trig functions, but we can do a similar domain restrictions, and we can define the inverse of those functions in a similar way. But we're going to have an entire section later on when we talk about derivatives of inverse trig functions, and we'll just kind of highlight all the things we need to know about the other trig functions at that time. So if you remember from pre-calculus, one of everybody's favorite topics is trig identities. And I have a hard time remembering the trig identities. There's a bunch of them. A lot of them are more or less the same, Some of them are different. I've listed 3 here that I think kind of encompass everything you need to know. And I'll tell you that if there's one trig identity I would memorize and not forget, it's this one. And it's actually not too hard to memorize because it really is just the Pythagorean theorem. If you look back on the unit circle, the x-coordinate and the y-coordinate form the legs of a right triangle with hypotenuse 1 because you're on the unit circle. But these other 2 are also important as well. And they're the sum identities or angle addition identities for sine and cosine that are also really important. And we'll see how these can be applied in just a minute when we do some examples. But also, first of all, I want to notice something else from the unit circle. And it's also going to give us a chance to introduce another idea that we need to introduce about functions, and that's the concept of even and odd functions. So notice from the unit circle that if I look at the negative angle, and so what I mean by the negative angle is if I look at an angle going counterclockwise, look at the corresponding angle going clockwise, notice that the cosine of those angles will be the same. So if I make the argument of cosine, or the angle, negative, that's not going to change the x-coordinate. It's just going to be a reflection over the x-axis. The x-coordinate doesn't change. But the y-coordinate will, because I'm reflecting over the x-axis when I make the argument negative. And again, just look back at the unit circle and you'll see what I mean. If I take a counterclockwise angle and the same clockwise angle from the positive x-axis, the y-coordinates are going to be negative. One's going to be positive and one's going to be negative. So a function f is called even if it has this property that cosine is illustrating. If I make the argument negative, it doesn't change the value of the function. And then a function is called odd if it satisfies this property that sine satisfies. If when I make the argument negative, it makes the entire function negative. And these ideas are going to be important. You could probably live without them, but they make a lot of problems later on really easy if you can remember certain properties about even and odd functions. And so cosine and sine are kind of marquee examples of even and odd functions. Other examples of even functions are power functions with even exponents. And then, of course, maybe that's where the terms even and odd come from. So for instance, x squared is an even function, whereas x cubed is an odd function. And then any power function with an odd exponent is going to be odd. So there's another couple examples here. So this is a lot of information, but all of these things are going to be useful later on. And even if we don't memorize them now, we want to be able to reference back some of these trigonometric identities and some of these basic properties of the trig functions. So this is a table of some common trigonometric values. Now, where do these come from? You may ask, okay, well, where does pi over 6, pi over 4, pi over 3, 3 pi over 4, 7 pi over 6, what's so special about these angles? Well, they're actually coming back from 45, 45, 90 triangles and 30, 60, 90 triangles. So if you remember, if you have a triangle, a right triangle, where these two sides are congruent, so these two angles are congruent right here, this is called a 45, 45, 90 triangle. And so this angle 45 is really pi over 4. so 45 degrees or pi over 4, and we have some special values. So if this leg is a, this leg is also going to be a, and this leg is going to be square root of 2a by the Pythagorean theorem. So we had this sort of special relationship with 45, 45, 90 triangles, and that's where these trig values are really coming from. So pi over 4, this 1 over root 2, is really coming from this root 2 in the 45, 45, 90 triangle. Similarly, we had a 30, 60, 90 triangle. So that was where this angle was 30 degrees. And in that case, if this was, say, A, okay, then this was going to be twice A, and then this was going to be square root of 3A. And then that's where these values are coming from here. For pi over 3, okay, so that's 30 degrees. Pi over 6 is really 60 degrees, so this angle is going to be 60 degrees. So these special values are just coming from 45, 45, 90 triangles and 30, 60, 90 triangles. And using that Pythagorean identity as well. So, if you're wondering, where does this 2a come from? Where does this square root of 3a come from? It's coming from the Pythagorean identity that, okay, if I square this and I square this, it better be this squared. Same thing here. If I square this and I square this, add them together, it better be that squared. So again, it's useful to have a table of these values. Whether or not you need to memorize them is kind of up to you, and maybe whether or not that's required for you. I'd say that it's worth memorizing because these values come up a lot. But if nothing else, you should have a table of them handy when you're solving problems. So the last thing we want to review from pre-calculus are exponential functions. So we've talked about polynomials, we've talked about trigonometric functions, just briefly anyways. So let's talk about exponential functions. In an exponential function, well, first of all, it represents exponential growth, hence the word exponential. But an exponential function has the following form. It's a fixed number a raised to a variable x power. So here a is going to be a real number, but we're not going to just let it be any real number. It needs to be a positive number other than 1. So a is greater than 0, and a is not equal to 1. And the reason we require that a not be equal to 1 is not necessarily clear right now. So if I let a be 1, well, 1 to anything is just going to be 1. So it seems like we would just get the constant function 1. But we want to exclude that case because we actually want exponential functions to be 1-to-1 or invertible. And so just a couple of notes about exponential functions. The domain of an exponential function is all real numbers. There's no problem in the domain. And the range of any exponential function is going to be 0 to infinity, not including 0, so just the positive numbers. So another important thing to note about exponential functions is their end behavior. And we're going to break this down into two cases. So the first case is when a is strictly greater than 1. And in this case, our function is really growing exponentially. So it's starting at 0, down at negative infinity, and it's growing. And when we get to the positive numbers, it shoots off to infinity really quickly. It grows exponentially. So as x goes to minus infinity, the function is going to 0. And as x goes to infinity, the function is going off to infinity very rapidly. Another thing to note is that exponential functions cross the y-axis at 1. Because if I plug in 0 for x, anything to the 0th power is just 1. Now if a is less than 1, the exact opposite thing happens. The function is actually going to exhibit exponential decay. And so it's actually going to start very large when it's negative, and it's going to decay off to 0 as x goes to infinity. So now as x goes to minus infinity, the function blows up to infinity very fast. But as x goes to infinity, the function actually levels off very slowly towards 0, never quite reaching 0. So you can see that these two cases are just reflections of each other. Okay, so here we have some basic properties of exponents. And these are really important when you're dealing with exponential functions to remember. So for instance, if I take this number a, so the number a is sometimes called the base of the exponential function. So if I take the base and I raise it to the sum of two numbers, that's the same thing as just taking the base to each number and multiplying them together. And if I take the base to a number and then raise it to another number, that's the same as raising the base to the product of those two numbers. And if I take two different bases, a and b, and multiply them together and raise that product to a number, well, that's the same as just raising each of the base to that number and multiply them together. And then finally, if I make whatever the exponent is negative, that's the same as just taking the reciprocal. So 1 over a to the x. So these are just some important properties to remember. Again, you'll probably have to review them, which is fine. Again, the most difficult part is just remembering this massive amount of information, because you'll be doing a problem and I'll say something like, oh yeah, well, you just do, if I have 2 to the, say, x plus y, and I say that's 2 to the x times 2 to the y, you may think, oh, where does that come from? Well, I'm just using these properties that are probably somewhere deep in the back of your mind. So just remember that they exist and we'll reference them when we need them. So let's talk a little bit about the fact that exponential functions are one-to-one. And this is a result that you can actually show just using the properties of exponential functions. But it's very useful because remember, the reason we care that a function is one-to-one is that means that they have inverses. And so this is actually going to bring up logarithms. And so maybe you haven't made this connection, but it's a very important connection, that logarithms, if you can understand exponential functions, logarithms are simply just the inverse of exponential functions. And that's really the best way to think about them. So recall, if I have my function a to the x with domain all real numbers and the range 0 to infinity, then because it's one-to-one, there's an inverse. And the inverse, now remember this number a is called the base of the exponential. It's also going to be the base of the logarithm that is the inverse of that exponential function. So this is log base a of x. And so it's really defined, this logarithm is just defined to cancel out the exponential. So if I take log base a of a to the x, I get x. And if I raise a to the log base a of x, I also just get x. So we're going to use these properties all the time. And so it's really important to remember that these are just inverse functions of each other. Now this is a great time to mention a very special base. So that base is e. And e is just a number. It's 2.7, I'll give you a few of the digits, 2.71828, etc. There are infinitely more digits. It's sort of like pi. It's irrational. It just has a lot of digits. It just goes on forever. There are computers right now trying to list out as many possible digits of e, but this is just a number. And it really seems like a very random number, but it is a valid base for an exponential function. So if f of x is e to the x, then the inverse is log base e of x, but we actually give this a special name, ln of x, so the natural logarithm. So that's log base e, where e is this number 2.71828, etc. Also, sometimes you'll just see log with no subscript, no base. That's understood, at least in most contexts, to mean log base 10. So if you ever see log by itself with no base, it's log base 10. If you see this ln, natural log, that's log base e. So let's review a few more properties of the logarithm function. So first of all, remember, let's say that now our function is log base a of x, where a is a positive number other than 1. If a is 1, this function is not well defined. So let's see. What does this function look like? Well, recall that because we know the domain and range of the inverse function, a to the x, we know the domain and range of this function. So the domain of the logarithm to base a is going to be the same as the range of the exponential base a, and the range is going to be the same as the domain. Let's not do the blackboard there. So the range of the logarithm is going to be the same as the domain of the exponential. And if you recall that exponential functions, when you graph them, are just reflections over the line y equals x. So the logarithm function should look something like this. And this is actually going off to infinity as x goes to infinity. Okay. And another important thing to note is that no matter what the base is, the logarithm is going to cross the x-axis at x equals 1. So that's x equals 1 right there. So that's important to remember. So that's kind of what the shape of the logarithm graph looks like. It's really going to be important later to remember what the end behavior of the logarithm is. So as x gets closer and closer to 0, the logarithm function is actually going to minus infinity. And as x goes to infinity, the logarithm is going off to infinity. Very, very slowly, but we'll talk a lot more about that when we get actually into the calculus of the logarithm functions. So the final thing we want to talk about with logarithms right now is the basic properties, just like we talked about with exponentials. And all of these actually come from the corresponding property for exponentials, just applied using the inverse instead of the function. So not really much to say here other than we're going to use these a lot later, and so you should just not be surprised when we see logarithms and we use certain properties. And if you don't have these memorized, we'll just review them real quick. I would do some problems with logarithms to familiarize yourself with these properties. So logs take products to sums. So the log of a product is the sum of the logarithms. Logs takes exponents to exponentiation to products. So if I raise a number to another number and I take the logarithm, that's the same as just multiplying the exponent times the logarithm. This one is really important. This is called the change of base. So later on, what we're going to do is we're going to almost exclusively use the natural logarithm. And there's really not a good reason why we're going to do that other than it's going to standardize everything, and the natural logarithm has some really nice properties. So if we ever have like log base 4 or log base 10, what we're probably going to do is we're probably going to immediately change to the natural logarithm. And this is how you do that. So if I want, or if I have log base 2 of x and I want the natural log, then it's just natural log of x divided by natural log of 2. And we'll see more examples of that later. And then this property just takes, okay, so reciprocals log, we'll just pick up a negative. And so these are the properties of the logarithm. All right, everybody's favorite game, solving trigonometric equations. And now, one thing to kind of notice is that we have to put this restriction here that theta lies between 0 and 2 pi. Now, it might have been something else, but if we don't put a restriction, trigonometric equations like this actually have infinitely many solutions because they're what's called periodic. So if I just keep adding 2 pi to my solution, I'm just going to get a new unique solution. But that's why we're truncating the angles to be just in one rotation as we go around the unit circle, from 0 all the way to 2 pi, where we started. Okay, so if we want to solve this equation, we just want to isolate theta. And so notice that when we write sine squared theta like this, what this really means is it's sine of theta all squared. And now we just kind of want to use order of operations to reverse this process. So this is something squared, so let's take the square root. Now I'm taking the square root of something squared. This is very important to remember, and you're seeing why this is important, because we're going to see things like this a lot. This is not sine theta. It's actually absolute value of sine theta. So I have something squared, and I take the square root. It's just absolute value of that something. The square root of 3 over 4 is really just the square root of 3 over 4. And I can write that as the square root of 3 over the square root of 2, using properties of exponentials. Sorry, over the square root of 4, which is 2. So this is just square root of 3 divided by square root of 4, but square root of 4 is 2. And so now remember, with absolute value, I have to think about two cases. Either sine theta is square root of 3 over 2, or negative sine theta is square root of 3 over 2. Okay, so then we just got to go back to the unit circle, the common values. So when is sine equal to square root of 3 over 2, or when is sine theta equal to negative square root of 3 over 2? Well, if I just look at my table of values, it's pretty easy. You have theta can be pi over 3. That's going to give me root 3 over 2. We can have 2 pi over 3. That's also going to give me root 3 over 2. Or, on the lower half of the unit circle, I have 4 pi over 3. That's going to give me a y value of negative root 3 over 2. And then finally, we have 5 pi over 3. That's also going to give me a value of negative root 3 over 2. So we actually have 4 solutions to this equation. And now notice that all of these solutions come from just going around the circle one time. In other words, these angles are between 0 and 2 pi. So here we have another equation involving cosine theta, and we're trying to solve theta between 0 and 2 pi. So the goal is to isolate theta, or in other words, isolate cosine theta. But here we actually have a problem because this is cosine 2 theta and this is cosine theta. We really don't have a way to combine those two quantities. But this is what we can do. We can actually use a trig identity. So cosine 2 theta is really the same thing as cosine of theta plus theta. But if I use the cosine sum formula, the angle addition formula, this is cosine squared theta minus sine squared theta. So really this equation is cosine squared theta minus sine squared theta plus cosine theta equals 0. But I can go a step further. I can write sine squared theta really negative sine squared theta as follows. 1 cosine squared theta minus 1. And this is coming from the Pythagorean identity. I'm just rearranging this equation. Sine squared theta plus cosine squared theta equals 1. I just subtracted sine squared and then subtracted 1. So I can replace negative sine squared theta with cosine squared theta minus 1. So I have cosine squared theta plus, because I absorbed this minus, cosine squared theta minus 1 plus cosine theta. Or in other words, 2 cosine squared theta plus cosine theta minus 1 equals 0. Okay, so why did I do all that work? Is this really so much better than what I started with? Well, yes, because let's say that y is equal to cosine theta. Or let's do x. Here. Erase that, so we'll have x is cosine theta. I could have done y, but I just wanted to use x. So this is really like 2x squared plus x minus 1. But this is a quadratic equation. And actually, it factors. This is 2x minus 1, and then x plus 1. And you can verify that when I FOIL this out, I get the same thing. Okay, but that means that to cosine theta, if I plug back in cosine for x, minus 1 times cosine theta plus 1 equals 0. So I have a product of two factors equaling 0. I can use the zero product property and conclude that either 2 cosine theta minus 1 is 0, or cosine theta plus 1 is 0. But this just means cosine theta is 1/2, and this just means cosine theta is negative 1. So I'm looking for values of theta between 0 and 2 pi for which cosine theta is either 1/2 or negative 1. But we can just look at the unit circle and list those out. We have pi over 3. That's going to give me 1/2. We have pi. That's going to give me negative 1. And then finally, we also have 5 pi over 3. That's again going to give me an x-coordinate of 1/2. So here are my solutions to this equation between 0 and 2 pi. So here you're going to see the value of knowing some common values on the unit circle. So those values that came from the 30, 60, 90 and the 45, 45, 90 triangle. Because let's say we want the exact value of cosine squared of pi over 8. Well, pi over 8 isn't on my list of common values from the unit circle. So what in the world do I do? Well, notice we can do something kind of silly. I'm going to say cosine of pi over 4 is equal to cosine of pi over 8 plus pi over 8. Okay, that's great. But I know what cosine of pi over 4 is. That's square root of 3 over 2. Nope. That's 1 over square root of 2. There we go. Okay, well, how is this helping me at all? Well, I can use the angle addition formula here for cosine. This is cosine squared pi over 8 minus sine squared pi over 8. But, okay, I'm looking for cosine squared pi over 8. I don't know what sine squared pi over 8 is. But remember, I can also use the Pythagorean identity. Because negative sine squared, we've already seen this, is actually cosine squared plus 1. So I have this equation. 1 over square root of 2 is equal to 2 cosine squared pi over 8 plus, I think that's supposed to be minus 1. Yeah, because negative sine squared, this will probably help you too. So sine squared plus cosine squared equals 1. So if I solve for negative sine squared, I should have cosine squared minus 1. Yeah, so that should be a negative. So this is minus 1. And then I can just solve for cosine squared pi over 8. So I can add 1 and then divide by 2. So I have 1 over square root of 2 plus 1, all divided by 2. So this is the answer. And now you may ask the question, why would I ever think to do this? This was very strange. I found what cosine squared of pi over 8 was by considering cosine of pi over 4. Well, I'm not saying that this is something you're going to do all the time, but I think this is a useful snapshot to show you that knowing some of these special values really can allow you to find other values of different angles. So this is going to be an example of an exponential function, and I'll show you why. So we have that a population of bacteria doubles every 30 minutes. So if we think about this, we're starting with one bacterium, which is just the singular of bacteria. So at t equals 0, we have 1. Let's say that p of t is the number after t minutes. So what I'm really doing here is I'm going to make a table of values. So we have t, and then we'll have p of t. So at 0, we have 1, and it doubles, okay, every 30 minutes. So after 30 minutes, there should be 2, and then after another 30 minutes, so after 60 total minutes, there should be 4, and then after 90, there should be 8, etc. Okay, so why did I do that? Well, that actually helps me figure out what P of t is, because notice that every 30 minutes, we're going to double. So that means P of t should be, well, what I started with, 1, and then times 2. How many times am I going to multiply by 2? Well, I'm going to multiply by 2 once for every 30 minutes. So I'm going to put t divided by 30. Because when t is 30, I'm going to get 2 to the first, so I'll get 2. When t is 60, I'll have t to the second, which is 4. When t is 90, I'll have t cubed, which is 8, etc. So P of t is just 2 to the t divided by 30. Okay, so this is an exponential function. Now I want to know how long it will take for the bacteria to reach a population of 100. So in other words, I want to find t for which P of t equals 100. So in other words, I want 100 to be 2 to the t over 30, and I need to solve for t. So this is going to illustrate the inverse relationship between exponentials and logarithms. I'm trying to solve for t. I need to isolate t. But t is up in the exponent of an exponential function. But what I can do is apply log base 2. And I'm using log base 2 because the base of the exponential is 2 to both sides. So in other words, this equation is equivalent to saying log base 2 of 100 is equal to log base 2 of 2 to the t over 30. But log base 2 of 2 to the t over 30 is just going to be t over 30, because the log base 2 and the exponential base 2 cancel out. And so then I just multiply both sides by 30. So I get that t is 30 times log base 2 of 100. Okay, well that's just a number. Let me tell you approximately what it is. It's going to be approximately 199.3 minutes. And there's our answer. So after, well, about 200 minutes, the population of this bacteria should be at 100. So we want to find this, the solution to this equation. So we want to solve for x. Now we have that the logarithm of something involving x is equal to 3. And to solve for x, we need to isolate x. So recall that the natural logarithm is log base e. So it seems like we should take e to both sides. So this equation should be equivalent to e to the log of 2x minus 1 equals e to the third. Okay, but e raised to the natural log, which is log base e, remember that natural log is really log base e, cancels. And so we have 2x minus 1 is equal to e to the third. But now I can just use addition and division. So I can add 1, so 2x is equal to e to the third plus 1, and then divide by 2. E to the third plus 1, all divided by 2. And this will be our final answer. So again, we're just using the inverse relationship between logarithms and exponentials. Okay, so we have another equation, and we want to solve for x. But this is actually going to illustrate something very interesting that can happen with equation solving. And we may see this from time to time, and it's something that we need to be very careful of when we're solving equations. But for now, let's just go in blind. Let's just say, okay, well, I want to solve this for x, so let me isolate x. And I'm going to be really clever, and I'm going to use properties of logarithms. I'm going to use the fact that if I'm adding two logarithms with the same base, I can just write them as a single logarithm with the arguments multiplied together. So I'm just writing this very clearly to say that, okay, the log, I'm adding these two together. These are all log base e's. And I can just multiply the arguments. Well, that's great, because now I can just do my favorite trick and so take both sides and put them in the argument of e. So e to this is equal to e to this. That should be equivalent. And then cancel the logs. I mean, if you think about it, you have log of something equals log of something else. We're actually just using the fact that log is 1 to 1. So if the logs of something are the same, then actually what you're taking the log of has to be the same. So in other words, x plus 6 times x minus 3 is equal to 10. But this is just a quadratic equation. And now be careful, don't use the zero product property here. Don't say either x plus 6 is 10 or x minus 3 is 10, because that only works if a product of two things equals 0. So I actually need to expand this out. So let's do that. So this is x squared. We have minus 3x plus 6x, so that's plus 3x minus 18 equals 10. I can subtract 10 over. Whenever you're solving a quadratic equation, or really any equation, it's always a good idea to get everything on one side, because now when I factor, notice that this does indeed factor. So we'll have x plus 7, x minus 4. I have a product of things equal to 0. And now I can use the zero product property. So either x plus 7 is 0, or x minus 4 is 0. And so we have two solutions, x equals negative 7 and x equals 4. But hold on. Hold the phone. We're missing something very important. And I'll pause for a second and see if you can tell me what it is. Of course, you can't actually tell me, but just think about it. So one of these solutions is actually invalid. So if I plug in x is equal to 4, I have log of 10 plus log of 1. That's going to be log of 10 plus 0, log of 1 is 0, equals log of 5 plus log of 2, which is log of 10. So x equals 4 works. But try to plug in negative 7. Log of negative 7 plus 6 is log of negative 1. But the domain of the logarithm function, remember, is only positive numbers. I can only plug in positive numbers into a logarithm. So something is going on here. It doesn't even make sense to plug in negative 7 into this equation. And the moral of the story is this. Always check your answers. So when you find answers, I mean, I'm guilty of not doing this all the time, but it's always a good idea to go and check back and make sure that your solutions are actually solutions. Because in this case, this guy is not a solution. We only have one solution, x is equal to 4. So this guy right here, this actually has a special name. This is called an extraneous solution. And an extraneous solution basically comes from doing something to the problem that actually wasn't 100% valid. So actually, when we applied these properties of the logarithms, there was actually something we needed to make sure of. And I'm not going to go into a lot of detail, but essentially doing this step, going from here to here, we actually introduced this extraneous solution. And that's okay as long as we check our answer and realize that, okay, x equals -7 isn't actually a solution. Only x is equal to 4 is a solution. So it's just, again, all of this stuff from pre-calculus is just something to keep in the back of your mind, because we're going to rapid fire when we get to calculus. We're just going to be doing algebra left and right, and all of these things are going to come to play from time to time.